All right, students. So I've been trying to, the last few classes, I've been trying to get you to really appreciate some of the beautiful things that we have in mathematics, and that it's one of those subjects that's sort of infinitely deep, and there's a lot of beauty the more you look at it. And if you slow down and try to appreciate patterns and connections, it's a lot more enjoyable to study math. And one pattern that I showed you is Pascal's triangle, which is a really great simple pattern that does a lot of complex stuff. And so here's the basic construction of it. And I want you to just see if you can see how I'm building this pattern. So I'm just going to write out the first couple rows of it. And I want you to realize, see if you can realize how I'm constructing this pattern here. All I'm doing is some pretty simple arithmetic. I hope you can see what's going on here. I'm going to pause for a second and just take a second and what do you notice and what do you wonder when you look at Pascal's triangle? There's a lot going on here. The first thing that I think just about everybody notices is that there's ones on the outside. Then most people are able to notice as well that the next diagonal row in is just the counting numbers or the natural numbers 1, 2, 3, 4, 5. So this row here has the number 6 on it. The next part's a little bit trickier, but some people find the pattern one way, which is noticing that this diagonal goes plus 2, plus 3, plus 4. So I would go plus 5 to get 15. Other people find the pattern by just saying, oh, look, the two numbers that are above add together to make the number that's down below. So all these little arrows that I'm drawing are just showing like 1 plus 3 is 4, 3 plus 3 is 6. So the number that would go down here, 10 plus 10, makes 20. 10 plus 5 makes 15. And so I encourage people to try to build this out yourself. It's just adding numbers. You can use a calculator if you want. But what I hope you notice is that each time you build a row, there are some actually really beautiful patterns that happen as you create it. Like I said, we have our counting numbers. We have that plus 1 or plus 2, plus 3, plus 4, plus 5, plus 6 pattern, where each time you're adding the value of the row above it. So here we have 1, 8, 28, 56, 70, 56, 28, 8, and 1. I hope you notice as well that there's a lot of nice symmetry going on here, that the left side of the triangle is going to look the same as the right side of the triangle. I'm going to scoot down just to see if I can fit in maybe two more rows here. 1, 9. Let's see, that makes 36. That makes, 84? I believe that's correct. That makes 100 and 26? 126. Then we got 84 because I know it's symmetrical. 36, 9, and 1. Let's just do one last one. 1, 10, 45. What does that make? 120? What does this make? 200 and 210? Then 126 and 126 makes 252, 210, 120, 45, 10, and 1. So one pattern that I think is really nice about Pascal's triangle is what actually happens when you add up all the numbers in that row. And so I'm going to call this top row, row 0. So then here we have row 1, row 2, row 3, row 4, row 5, row 6. And so the row number matches with the number right there on the second diagonal. Row 8, row 9, row 10. And one thing that I hope you notice is that when you add up all the numbers in the row, 1 plus 1 makes 2. 1 plus 2 plus 1 makes 4. So this is row 2. Row 3, 1 plus 3 plus 3 plus 1 makes 8. Row 4 adds up to 1 plus 4 plus 6 plus 4 plus 1 makes 16. And row 5, if you add it up, you end up getting 32. I hope you notice a pattern here. The value of the row, when you add it all up, is doubling. And so now I can actually even say row 6, I know it's going to be 64 because that's going to fit with the pattern. Row 7 is going to double to be 128. And I want you to think about, why is that the case? That the way we built this simple triangle doubles in value each time you go down below. And the reason is you're using all of the previous values to create the next row. That's how you create the next row, is you take the values from before and you add them together to make the next row. And so if you had 4 in the previous row, you're going to add 4 together to get 8 in the next row right there. And so similarly, I can move on and get 256, get 512, get 1024. One thing that's really nice is that you can actually shortcut this, because it gets a little annoying to actually write the number down. You can shortcut this and just write it as an exponent. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. What I'm noticing is that the row number matches up with the exponent. So anytime you want to know what the total of that row is, then you have the 2 raised to that exponent. And this should lead you to a conclusion that's hard for a lot of students. Row 0 has 1 number in it. And what does that mean? You have to conclude that 2 to the 0 power is equal to 1. It's the only number that makes sense in the pattern. 2 to the 0 has got to be equal to 1. There's one last thing that I wanted to show you here with Pascal's triangle. There's actually a lot more to learn about this. I could show you things about triagonal numbers. I could show you things, triangular numbers. I could show you things about three-dimensional shapes like tetrahedrons. I could show you things about how many routes you can take to get around the city. I could show you things about expanding binomials. There's a lot of really deep connections that you can make with this. But one last thing, because I was showing you fractals recently, one last thing is, if you go through and shade in all the even numbers like this, you'll notice a shape that we've seen before starts to show up. So I'm shading in the even numbers, making a triangle out of it, and you can even see the start of what's going on down here. But this shape right here should look familiar. This is the same shape that we were studying the other day, which is Sierpinski's triangle, where you have each successive construction of the triangle, you subtract out the middle triangle, and you're left over with 4 copies of the original shape. And you can imagine that as Pascal's triangle goes on forever and ever, it actually continues to create Sierpinski's triangle. And what I want you to think about is, why is that true? Why is it true that the even numbers form a little upside down triangle? Why is it true that the odd numbers sort of expand out in a different shape and the even numbers filter down in an upside down triangle like that? Something to think about. So I hope you enjoyed watching this. There are many, many, many more deep connections of Pascal's triangle. And if I get a chance, I'll make some more videos showing them to you. Feel free to ask questions.